Hello and welcome back to the second video about groups. In this video I want to show you the workflow of creating a script. So how do you add programs, how do you get data from one program to the next, and so on. So in the end you will have a script that does multiple things to achieve some goal you want. For this example we want to do a small specific task. We want to simulate an orbit for a low Earth orbiting satellite. We then want to visualize the tidal accelerations acting on the satellite throughout its orbits, and we want to plot this in a map. So it's a relatively simple task, which can be done with a few programs and groups. So I've already created a script file here. It's empty for now, except for some global variables which are part of our template. And yeah, so let's start. First of all, we want to add a program. You can just hit the add button here and select one. The first program we want to add is simulate orbit. So we have a filter here. So we type in simulate and we get simulate orbit. So this is our first program. Our program has several settings or input and output fields. And here everything marked with a red star indicates that this is a must-set field. Everything else is optional to some degree or another. Some of them have default values, others do not. But yeah, output file orbit is a must-set value, so we need to provide a file where the output is written to. So in principle, the principle of groups and groups programs is that programs possibly read data, but they usually always write data to some file, and the next program then can read this data. So let's start with writing our orbit. We'll just write it into a file called orbits.txt in the folder where the script is located. Input file satellite model. This is a model of the satellite, which describes its mass and geometry and so on. So as you can see here, the group's data dir variable is used in the curly braces. I'll talk about this more in the next video. This variable will be replaced by the global variable group's data dir. So I can select any satellite model. For this video, let's just use the one from Grace 1. And as you can see, the path beginning is still replaced by the group's data dir variable. So next we need a time series. So we need to provide the epochs for which the orbit is simulated. As you can see here, this is both mandatory and there are ellipses here. So this means I could provide multiple fields. So time series, we have several options to choose from. If we want a uniform sampling, time series, uniform interval, we want yearly time series or whatever from an instrument file, we will stick with uniform sampling. We will say time start. Here we can choose our global variables, time start and time end. We haven't set them yet, but we can do it. So let's say we want to simulate our orbit for 2020, so the 1st of January 2020. And time end, let's say we want to do 1 day. We could enter the date again, but what we can also do is just select time start and add +1. So the time fields are always given in modified Julian date, so it's in float days. So we can just select time start +1, and groups will know that this time start is the global variable time start. As you can see in the GUI, the date already gets parsed. So we know it is correct. And as you can see also here, where we link to these global variables, also the dates are already correct. And for a sampling, let's say we want to do a 1-minute sampling. Here the sampling is also in days. This is why it is entered as 1 divided by 1440. Okay, so we could add another time series, but this is fine. We want to use these epochs. So this class time series will create epochs from time start to time end with 1-minute sampling. Okay, integration constants. We can use Kepler parameters or position velocity. Let's stick with, or a file. Let's stick with Kepler. Let's say we want to have a semi-major axis of around 7,000 kilometers, so about 700 kilometers above Earth's surface. Eccentricity, let's say 0, inclination, let's say 85 degrees. And for the purpose of this video, everything else, let's set it to 0. But of course, you could specify whatever you need here. Okay, next, orbit propagator, we'll just stick with polynomial. There are several others, Euler, Rummel-Kutta, and so on. Well, let's stick with the default one. Same with Earth rotation. There, the default EUP, rapid time series from the IRS is selected. We are fine with that. Ephemeриds, also fine with JPL. And what we then finally need to provide are forces that act on the satellite. First of all, we need a gravity field. So we can select here potential coefficients. And let's use GOCO 06S gravity field. So it's just a GFC file, which you can download, for example, from ICGEM. Max degree, let's set it to 60. So this is the spherical harmonics degree. For this example, it doesn't really matter. Let's keep it like that. For tides, let's add astronomical tides, so from planets and so on. Let's add Earth tide. The default settings are fine in this case. And let's also add Dudes and harmonic tides, so ocean tides. As you can see, that by default, ocean tides FES 2014b is already selected, so we are fine with that. We just stick to the default settings. And what we also going to add are MISC accelerations, in this case, solar radiation pressure. So this is why we need the satellite model, which describes the surfaces of the satellite and their optical properties, because we want to also simulate MISC accelerations in this example, so solar radiation pressure. Here, all the settings are fine as well. Okay, so this is the first program. This program will integrate an orbit based on the settings we chose, and we'll write the output to orbit.txt. Next, what we also need is the attitude of the satellite. So we can use a program called Simulate Star Camera to simulate a basic star camera, and this which observes the attitude. And this file just needs as an input file an orbit file, and as an output file, let's call the output file starcamera.txt. So it will take each epoch from this orbit and compute the associated star camera file. As you can see here in the description, the axis of this body frame, which is simulated, is X along track, Y cross track, and Z then in the radial direction. So we're fine with that. Maybe a different satellite needs a different system, but in this case, we're fine with that. Next, let's simulate an accelerometer. So this is what we wanted to do. We want to visualize the tidal accelerations acting on our satellite. So we again need an output file. Let's just call it accelerometer. We need, again, a satellite model. It should be the same as here, so we can just copy paste it. We need an input file orbit. We can use our orbit. We need the star camera. We can also provide here. Earth rotation, again, is fine. Ephemeриds are again fine. And for the forces, this is now which forces do we want to simulate. Only for this accelerometer. Here we can just use the ocean tides, because we're only interested in visualizing the ocean tides. So in this case, we will only copy the ocean tides, the Dudes and harmonic tide element from above. And yeah, that's it. So this program will generate or will simulate accelerometer measurements from tidal accelerations for the orbit we simulated using the star camera we simulated. So now we have all the data we need. We just need to visualize it, and we want to do it in a map using in the form of a ground track. So we can use the program orbit to ground tracks, which does exactly what it says. It needs an input file orbit. Let's again copy it from here. And it outputs a gridded data file. So it converts data to a grid, which we can plot on a map. Let's call it grid.txt. Earth rotation again is fine. So this program, like this, it only converts the orbit to a ground track. But since we also want to visualize our accelerometer data, we can add an additional input file instrument. You can see here this is an optional file, and it has the ellipses, so we can add one or more files. So I can add this. We could add additional files, and the values from this accelerometer file are get appended to the grid file. So it adds the columns from this file to this grid file. Okay, so far so good. Last program is .map. We want to visualize our data in a map. Let's call it groundtrack.png. We will skip the title, and now we can set different layers here. First of all, so we have a reference. Let's add a coast layer so we can see in the background the continents. I don't particularly like lines. I prefer to have colored ocean, and we can say, okay, the ocean should have the color light blue. Land color, we will skip it. It will be white or transparent. So this is our background layer, and then we can add a different layer. This is the same principle as any graphics program like Photoshop and so on. You just add layers, and they will get visualized on top of each other. So our next layer, we want to simulate or want to visualize our ground tracks. In this case, we want to use the layer points. We have one position each minute, so we will visualize them as points. As you can see here, we need an input file gridded data, which is the one we created here in output orbit to ground tracks. As a symbol, we will use a circle, and the color of the circle should be determined from the value. So if you set it to none, except you can of course choose any color, but if you set it to none, the color of the value will be determined from the value itself, as long as you set a color bar, which is enabled by default. And for data, you can see here on the right, it says input columns are data 0, data 1. So this grid file contains coordinates and then the additional columns for the accelerometer data. I'll show you later how this file looks like. But for now, we can, let's say we want to visualize the total acceleration. So we can say square root from data 0 squared plus data 1 squared plus data 2 squared. So this is an equation. Groups can parse equations, can parse mathematical expressions in most of the input fields. And we have 3 columns for X, Y, and Z, the accelerations along X, Y, and Z axis. And we just want to compute the total. And something else we want to do here is the values in simulate accelerometer, they get output in meters per second squared. So it's SI units. Since this will be very small values, we want to visualize them in nanometers per second squared. So we can just here multiply times 1 trillion. So we will convert the values to nanometers. You have to know that here in groups, usually in the plot programs, you have to do this in the values, because then later in the color bar, we could define our min and max in nanometers per second. But we will skip the min and max. We'll just add a label, acceleration in nanometers per second squared. Okay, that's pretty much it. We will leave all the other settings to our default values. Projection is fine, it's a Robinson projection. And yeah, let's see if it runs. One thing I forgot is I go into options and set transparent to no, since I'm using a black background in my file explorer. So okay, now let's run it. Everything is fine. As you can see, a command window opens. The orbit is simulated, 1 minute sampling. With tidal model can take a few seconds. It's done. Then next is simulate star camera, which was finished instantly. And next is simulate accelerometer, and then orbit to ground tracks and plot maps, and it's already done. So we close it and go to our directory. We can see there's now a ground track plot created, and it is basically what I expected. We can see a map in the background with light blue oceans, and each point is a point along the orbit. So as we had a 85 degrees of inclination, it's almost a polar orbit. It's pretty close to Earth, so we have several revolutions for this one day, and tidal accelerations are of course largest over the oceans, especially close to the coasts. So this is what I expected. Okay, that's it for this video. In the next video, we'll talk about the parser in groups, how you can parse global variables and other variables and use them in your scripts. So thanks again for watching, and see you in the next video.